Hi and welcome to the video lecture series on thin film flow modeling and simulation in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work at the Division of Machine Elements here at Luleå University of Technology. Now this is the second part which involves the discretization of the Reynolds equation, and it's of the fourth video lecture on the application of the finite difference method. The sources of literature in this topic are many, and I've chosen only to list the course compendium section 5.6, which is exactly on the discretization of the Reynolds equation by means of the finite difference method. But for the interested reader, I've also chosen to list the book Multi-Level Methods in Lubrication, which also involves quite a lot of detail and important such on the discretization. We will now consider the discretization of the Reynolds equation in 1D. In 1D, the stationary Reynolds equation is just a Poisson type of ordinary differential equation, and it can be formulated like this. So we have ddx of a coefficient function epsilon times the pdx equal the right hand side dc dx, and the domain of consideration is xa and xa to xb. Now for the Reynolds equation, to have the Reynolds equation exactly, we need to specify the coefficient function epsilon exactly like this, and the right hand side coefficient c exactly like this. Together with the boundary conditions, if we consider them to be of Dirichlet type, so that we know the pressure at each boundary, we can at least numerically solve this problem, and schematically we can obtain a solution looking like this in terms of pressure. So we have the boundary condition PA at the left boundary where x is xa, and boundary condition PB at the right boundary where x is xb. A discretized version of the Reynolds equation in 1D can be obtained by generalizing the derivation that we had before on the finite difference scheme for the second derivative. And to do this, so let's let then G be epsilon p prime of x, and we use the central difference in the intermediate nodes, the half spacing interval, and then we just by that central difference immediately obtain this expression for the derivative g prime in point xi. Now let us use the following definition for the coefficient function epsilon at these nodes xi plus minus delta x half. So we take it as an average of the values in the nodes xi plus 1 on the plus side, and xi and xi minus I on the minus side. So this is an approximation, and it can be chosen differently. The arithmetic mean value is one way of choosing it, which has been done now. Okay, so what remains then is to use the central difference again to approximate p prime of x at the half-spaced nodes xi plus minus delta x half. So we do it again both for the xi plus delta x half and xi minus delta x half points. Then we have this one. This means that the left-hand side of the Reynolds equation or the Poisson equation may be discretized with this second-order accurate finite difference scheme, as we see here, and in one way of formulating it, and then in terms of what we defined about epsilon, so the arithmetic mean for the values in the half nodes, and we use the central differences for the pressure derivative in the half nodes, both sides. Then we obtain this, which we of course can combine and write like we have here below, and we have three coefficients for the terms, or for the pressure in the points xi minus 1, we have one coefficient, and then for the point xi we have another coefficient, and then for p in the point xi plus 1 we have the third coefficient. And all of this is divided by 2 delta x squared. And we remember that epsilon is the epsilon I plus minus half is the arithmetic mean of epsilon in the nodes on each side of the half node. The right hand side is readily discretized by a central difference, for which it becomes exactly this expression. The lubrication problem may however become hyperbolic in certain cases, and one of them is when the viscosity becomes very high in the EHL conjunction and the film thickness at the same time will be very small, and therefore the cube of the film thickness will be incredibly small, and dividing this with a large number mu will make the coefficient vanishingly small. Another case is when cavitation appears and the pressure can be assumed to be more or less constant in the cavitated region, then the pressure derivative disappears there, and the problem becomes hyperbolic due to that. So in both these situations, epsilon times the pdx becomes vanishingly small. And in order to solve now the problem in these cases, we have to introduce an upwind difference for the right hand side. The central difference cannot capture the hyperbolic nature of the problem in this case. So the full finite difference scheme for the Reynolds equation, or the Poisson class of differential equations, to which it belongs, may be therefore be formulated as precisely like this, very simplistic in terms of index notation, and we have three coefficients, one for pi minus 1, another one for pi, and another one for a third one for pi plus 1, and then we have a right hand side vector for each grid point I. So the coefficients AWI, AOI, and AEI are just functions of the coefficient function epsilon and the mesh size delta x. And the right hand side is either the central difference or the upwind difference, dependent on the type of flow. And all these coefficients are known if we know the film thickness, the viscosity, the density, and the velocity of the velocities of the surfaces. Otherwise, they are not known, and we can linearize the system using some kind of fixed point iteration scheme. So now the points x naught and xn plus 1 sits on the boundaries of the domain, where we know the solution P, but the solution outside that is undefined, and this means that this finite difference scheme for the pressure is only defined for the interior points xi, so for I equal 1 to n. So we highlight that with some color here, and we also express now a few of the equations. So the equations for I equal 1, 2 and n are given below here, and then you can probably guess the intermediate equations in between. So this specify the determining system of the problem. However, we have to notice that in the first equation here we have a boundary condition, and this is a known pressure, and we cannot solve the system of equations for something which is already known. So this has to be moved into the right hand side, and the same goes for the last equation here, the one for I equal n. There we have the other boundary condition at xb, where n is and where we have xn plus 1. So both these needs to be moved into the right hand side of the equation, and this is actually a determining system which can be formulated in matrix form as a tri-diagonal system. So we have 3 diagonals, non-zero diagonals, and then the rest of the matrix is just zeros. Now you can see in the first row of the right hand side vector we have the boundary condition for the XA boundary, and on the last row we have it for the XB boundary. Now, just in compact notation, we can formulate the matrix here, calling it the determining matrix A, and then we have A times P equal F, where F is the right hand side vector. And now, if this were numerical values, we could be solving it readily in MATLAB with the backslash operator, or with matrix inversion and multiplication if we like. Let us now have a look at an example, and let us make this as simple as possible but as general as necessary. And I would say this Poisson type of equation as we have here is precisely this. So we have a very simple one, but still with a non-zero right hand side. It's actually a cosinus function, and it's defined on the interval from 0 to 4, and the reason for this has to do with the discretization we will choose later on. But let's see, we have chosen homogeneous, not homogeneous, but Dirichlet boundary conditions, and they are that the P is 1 on each side, so P at 0 is 1 and P at 4 is 1. And now if we discretize this problem with 4 elements, so n is 4, that means that delta x, the mesh size, is exactly 1. Now we can discretize this problem, and we do this by applying the finite difference scheme that we derived before, so which we have here, and we recall that the coefficients are given by the epsilon function, and the epsilon is approximated by its arithmetic mean value, like we have here. Now for the problem at hand, we had delta x equal 1 and we identify epsilon equal to 1 directly from the problem. Recall, it was just the second derivative of p. So epsilon must be 1. Now the right hand side in discrete form is just gi in the points xi. So all this means that the coefficients a wi, a naught I, and aei are just most simplistic numbers, 1, minus 2, and 1 respectively. And moreover, we can equate the right hand side vector by the expression for gi directly, and well, the boundary conditions also, of course. So the right hand side vector just becomes minus 1 pi squared over 4 and minus 1. In matrix form, the system for this specific problem just becomes a 3 by 3 matrix for the internal function values p1, p2, and p3, and we have the right hand side vector over here, and the solution is readily obtained in, for example, MATLAB, just by entering the matrix as we see here, the right hand side vector as we see here, and obtaining the pressure of the solution P at the internal nodes. That's the reason for the underscore int addition to P by the backslash operator, and then just we take the transpose of it just to print it as a row vector, not to take up too much space. So P in just becomes these values. We can see it's symmetric in the middle, over the middle of the interval. And here we have a slightly generalized example. So it is the same equation, but now we take a little bit more care and we specify the number of nodes, the number of elements, we specify the length of the domain, and we can specify the boundary conditions. And then we pre-process this data, so we define the delta x, the mesh size, like just L over n, and then we define the discrete grid with the use of linspace operator. And we recall that we have now n plus 1 nodes, since we have n elements. And then we do an analytical solution, because we know that the analytical solution to this problem is just cosine 2 pi x over L. And then we set up the system in general, and it can be done like this with the diag, which is just creating a matrix with a diagonal, and you position diagonals in the second argument of this, and the first part is just a vector containing the elements of it. And then you can add these diagonals together, and we have to remember the mesh size. In the 4 element case, it was just 1, but here when we have 2 to the power 6 elements, it will not be 1, and therefore we need to divide by dx squared. Then we do the right hand side vector, and it's nearly as simple as before. We just define it now, and we can base it on the analytical solution, as it's just the coefficient minus 2 pi over L squared times the analytical solution, which is the right hand side of the Poisson equation that we consider. We also add the boundary conditions to the right hand side vector, and then we can solve it in MATLAB, and we can also visualize the results. And here you can see a few different results obtained with different number of nodes. So when we had 4 nodes, you get these 3 values, the 3 solution values plus the boundary conditions. So 5 nodes in total, but only 3 that we solved for. And then increase the number of nodes, and you see a smoother and smoother solution, which of course converges to the analytical solution. We can measure this by means of outputting some error measure, and in this case for 64 elements we have an error of 0.0012, so it's already now a pretty accurate solution. We are by now quite familiar with the Reynolds equation, and this is the one in 2D, and of course we can do the same and just comprise all the functions rho, h and mu into a coefficient epsilon, but we need perhaps one in both directions if we want to be very general and in the end also cover a polar coordinate system for our Reynolds equation. So we look at the Poisson, second order type of Poisson equation here on the right, with epsilon x and epsilon y as coefficient functions in the Poisson flow terms, and then we have dc dx at the right hand side. So it's we are still confining our problem to having a motion, relative motion between the surfaces in one direction only. The rest of what you see here on the slide is things you know, and since we consider the Newtonian isothermal fluid, rho and mu are constants, so we know epsilon x and epsilon y and c for all x and y values. To accomplish discretization in 2D, we have to number our nodes in a specific way. We've already seen this for the contact mechanics problem. What you see here in green are what we will be referring to as internal nodes later on. Very important, of course, as you saw with a one-dimensional problem. And we have numbered them in a specific way here. So we increase the I index for the x direction first. So we go 1, 1 with I and j starting 1, 1, and then we increase I to 2, keep j 1, so we go 2, 1, and then we increase I again 3, 1, and then we increase j, so we have on the second row in our matrix here, our discrete grid, we have 1, 2, and then we increase j, so we have 2, 2, we increase j again. I haven't written out that point here, but it would be 3, 2, and then we increase the j index again, and we have 1, 3, and so forth. And we number all these nodes marked here in green, and these will be referred to as internal nodes, and it's very important as these are the nodes that we solve for. In 1D, you remember we made finite differences over 3 indexes for the second derivative term. But in 2D, we have 2 directions, and that means we have finite differences of 3 indices in both directions, and that's why we get a 5-point discretization scheme for a 2D problem, Poisson type of problem like the one we are considering. So with the center at the node ij, we then have this 5-point scheme with a west and east and south and north connected node, and these are the nodes required to make finite difference scheme for both the two Poisson terms containing epsilon x and epsilon y functions, as we will see on the next slide. Let us start by considering the ddx epsilon dp dx term of the left hand side, which we can discretize with the central difference that we have derived before. So it starts at xi minus 1/2 and it ends at xi plus 1/2. And because of this, and assuming that the epsilon function, the value of the epsilon function at this half grid spacing can be taken as the arithmetic mean, we can easily obtain the following expression, which we have sorted a little bit on the bottom line here. And if we do some information hiding, we can create these west and east and central coefficients like this. Similarly, we can carry out the same type of discretization for the ddy epsilon dp dy component, and finally we can comprise that in terms of coefficients south and north and central like this. So the only difference between the terms is that we in the x direction vary the I index, and in the y direction the j index. And due to this, we end up with schemes for south and north, in the south-north direction in the y direction, and then in the west-east direction for the x direction, where the index varies in I. So similar to 1D case, we get a finite difference stencil for here then for I and j, and we can express it in terms of these coefficient functions east, west, south, north, and the central one. So that's the left hand side, and the right hand side is just Fij. And these coefficients, or especially the central coefficient here, is comprised from the central x and central y coefficients together, and therefore it is actually expressed in terms of the east and west coefficients like this, and it has a negative sign, remember that. And the right hand side, the discretization of this one depends on the type of flow, and in many cases we can have, or in many type of flow, it depends on the type of situation we apply this type of equation to, but in terms of the Reynolds equation, it's a type of flow. And the central one is okay as long as we don't go from elliptic to hyperbolic within the region, and if we do, we have to consider instead an upwind discretization scheme. In addition to the interior nodes, we have boundary nodes where the pressure is known, or at least if we have Dirichlet boundary conditions, then the pressure is known at the boundaries. And it is important to distinguish these ones, of course, because when we build the determining system, the known values of the pressure must go to the right hand side. Notice that with this 5-point type of discretization scheme, the corner points will be left out. So the value at the corners can be whatever they like, and they will not affect the solution of this system. A 5-point finite difference is one way of discretizing, but we could have also made use of more nodes in our discretization, and then the absolute corner points could also have entered the determining system and have had an effect on it. But here we consider the 5-point formula only. As we will see in details later, This determining system in this case will be a 5-diagonal matrix where the diagonals corresponds to this 5-point discretization scheme. So it will take this form. So it will be a sparse matrix, mostly zeros, but then there will have 5 non-zero diagonals in this fashion. And in more details, what enters those diagonals are of course then the values of the center coefficient, the east and the west coefficient, and the north and the south coefficient. In between the south and the west, there will be a whole bunch of zero diagonals, and the same between the east and the north will also be a whole bunch of zero diagonals. And then on the lower and upper triangular parts of the matrix will be all zeros. Should also be noticed that it will be zeros on the every n-1 row of the east and the west index due to boundary conditions. These coefficients multiplied by the known pressures will be moved to the right hand side. And you can also see at the very top of the matrix we will have a first west diagonal term, which is also moved to the zero, and at the bottom there will be an east coefficient times the pressure at the exit boundary, the east boundary, going to the right hand side. One can also view this determining matrix AD as a block matrix, and it can be seen here. So we can construct the blocks for each diagonal or each part of these 3 sets of diagonals like this. We have block matrices with one main diagonal, rest is zeros for the south coefficients, and then we have block matrices containing the east, central and west indices, and upper and lower parts zeros, and then another one block matrix with a main diagonal for the north indices. The right hand side vectors will contain not only the Fij values, it will also contain the coefficients times the boundary conditions. And it will be looking like this. So at the first block, because this is also a block construction, but a block vector construction one can think of. In the first block we will have the boundary conditions coming both from the south indices and from the east, from the west and the east indices in the first row and last row of this block vector. And then there will be a central part of B of the right hand side vector where we only have the east and west boundaries contributing to the vector. And then on the bottom part, the last block vector, there we will have the north boundaries also included. And this actually means that there will be a zero vector in front of or preceding the diagonal for the south indices here, and it will also be one that proceeds that comes after the diagonal for the north indices, as you can see here, vector with zeros, because those indices have been moved over to the right hand side. So the determining system of equation will look like this, schematically at least, and we can solve it for the pressures at the internal nodes, and this type of system can be formulated or generalized for any type of Poisson equation of the form that we have above. And in detail, what we saw before, we also assumed that P, the solution P, was constant on the boundaries of the domain.